Good morning, everyone. Welcome to the 2024 Romanowski Lecture of the Royal Society of Canada. Bonjour, bienvenue à la Conférence Romanowski. The Miroslav Romanowski Medal in an annual lecture was established in 1994 at the generous bequest of the estate of internationally renowned metrologists. So I'm challenging some of you to know what metrologist is. We're in the Academy of Science. And the metrologist Miroslav Romanowski. The recipient selected for this award has made significant contribution to the resolution of scientific aspects of environmental problems or for important improvement to the quality of an ecosystem in all aspects, terrestrial, atmospheric, and aqueous, brought about by scientific means. Ce prix vise à reconnaître une contribution importante à l'explication scientifique de problèmes environnementaux ou à reconnaître l'amélioration notable par des moyens scientifiques de la qualité d'un écosystème, sous ses aspects terrestres, atmosphériques et aquatiques. Professor Abdelhamid Sayari, from the Department of Chemistry and Biomolecular Sciences at University of Ottawa, was awarded the 2023. This is not a mistake. The awardee gets the prize the year after at the COE presents the talk. So 2023 Romanowski Medal. He is one of Canada's most cited chemists for his pioneering work on porous material and their environmental application. He is internationally recognized for the discovery and development of recyclable materials for carbon capture with unparalleled efficiency. Thanks to the high selectivity and low regeneration energy of Prof. Sayari's proprietary materials, his invention is poised to become the leading technology for CO2 capture with direct implication on greenhouse gas effect in global warming. So there'll be time to have questions at the end if we are on time. We have to leave the room at 9 o'clock, so I certainly will not want to push him to do faster, but hopefully we can have a few questions. So I'll stand here, a few minutes before we have time to go. So, ladies and gentlemen, mesdames et messieurs, please welcome Professor Abdelhamid Sayari. You have the
No, I don't. They give it to me.
There you go.
Okay.
That should work. Okay.
Okay, bonjour tout le monde. Good morning, everyone. First, I would like to thank the Royal Society of Chemistry for giving me this nice award. And today in my presentation, I am going to talk about the CO2 capture technology as it relates to global warming and climate change. And as you know, there are many, many aspects to climate change, and a lot of people are addressing it from different angles. So from decrease in greenhouse gas production to mitigation to adaptation and so on. But usually the main culprit is greenhouse gases. And even though CO2 is not the most potent greenhouse gas, but because of the sheer volume of CO2, it becomes the most important greenhouse gases. And unless we put some lid on CO2 emissions, I'm not sure we're going to get there. And this is a humongous problem, as you're going to see. So this story started, as you can see here, by an UNCERC grant that I got in 2001, where very few people were talking about CO2 capture. And I presented a project called the carbon dioxide scrubbing the dry route. And I will explain what the dry route means. So today, my job is to compress 23 years in 30 minutes. Okay. This is the main problem, is that we emit 40 gigaton of CO2. If we look at the highest production of any chemical, that is sulfuric acid. We make 265 million tons. So we need 150 years of production of sulfuric acid to have the same production as 1 year of CO2 emission. So that is how big this problem is. Let's assume that we want to remove only 10 gigatons of CO2. We will need 10,000 plants of 1 million gigaton each. So if we build them at 2 a week, it will take us several years to build them. So this is how big this problem is, but that does not mean we cannot face it, okay, and I'm trying. Okay, so the first problem we said is the CO2 emissions, how large is it? Then the industry does not exist, okay? It is now being built, that industry. We don't have industry for CO2 capture. We have industry for CO2 removal, and that's a different thing, and I will explain. Okay, this is the CO2 removal. This industry exists 70 or 80 years now, and it removes CO2 from high-value gases, like natural gas or hydrogen. And therefore, we afford to have a cost on this technology. But if you are removing CO2, or if you are capturing CO2 for the sake of capturing CO2, it has basically no value. Okay, so we are removing CO2 to make clean nitrogen, and we just let it go in the atmosphere. So that's why it is very costly to just capture CO2. But if you are removing CO2 from natural gas, it's fine. It can have a cost, and we add it to the cost of natural gas. Or if you are doing it to purify hydrogen, that's fine. If it has a cost, we put it on the cost of hydrogen. But if you are removing CO2 from flue gas that we usually just let go, then we have to try to decrease the cost as much as possible. And even that cost, it has to be paid by society, because there is no value to the CO2 we make. Well, there is some CO2 that has value, but most of the CO2 that we are trying to capture, we try to sequester. Okay, that is the issue, okay? Now, my objective, okay, what is the problem with this technology? We can use it it has been used for CO2 removal, we can use it for CO2 capture. The problem is it is very expensive, because if you see how it works, you have this green tower, that's where things happen. That's where we capture CO2, by mixing CO2 in a solution of amine. What's special about amine? As you can see in the bottom of that screen, the amine has a reversible chemistry with CO2. So when we combine CO2 with amine, we make some compound. But that compound is not very stable. So if we heat a little bit, we release the CO2 back. So what do? We remove CO2 from a mixture of gas, then we sequester it in this compound. Then after that, we take this compound and we release pure CO2. Then we can do whatever we want with that pure CO2. It's no longer mixed with natural gas or mixed. And up to now, or up to a few years ago, we just let it go, because the objective was to remove it from natural gas, not to capture it, okay? But now we want to capture it and we want to sequester it, okay? So the blue one, the blue tower, regenerate the amine solution. And in order to regenerate it, we need to heat it. But that amine solution is 70% water. So we are heating water. That's why this technology is expensive. So we need to copy that technology in a new technology that requires less energy. So I want to remove the water and replace it by solid material. And that's where my expertise come to play, because at that time, and I am still have lot of knowledge in nanoporous materials. These nanoporous materials are materials that have very, very, very tiny channels. As you can see, their diameter is about 10 nanometer. And for those who want me to remind them, 1 nanometer is you take 1 millimeter. Everybody is familiar with 1 millimeter, and you cut it in 1 million pieces, and that's a nanometer. So these pores are very tiny, and they create a huge surface. And I need that surface to anchor my amine. Okay, so now I move from a liquid that have amine dissolved into it to a solid that is holding the amine groups. And I don't need to deal with any water at all. Okay, so I move from absorption, that is the removal of CO2 from a solution, to adsorption, that is the removal of CO2 using a solid material. So I'll be talking about adsorption using this kind of material. So how we connect amines to this kind of material. So there are 2 types of amines. The first group, you can see they have, don't think I have a pointer here, do I? But anyway, at the end of these molecules, you see this silicon something. So these molecules, they have their left part that can be anchored to a surface. The other are polymers. You can see, yeah? Yeah?
I think this
No, that's to go back.
no, sorry.
Yeah. That's fine, I can keep. So the other group that I call polyethylene, PI, these are polymers that are rich in amine groups. You see, every time you see nitrogen, it's an amine group. And the way to associate these type of molecules with the solid that I showed you, there are two ways. The first group, they are directly connected to the surface of silica. You see, the surface is rich with these OH groups, and they are directly connected. So we call this surface grafting method. The other group, we just deposit them in these channels. Because these are polymers, we drive them inside those channels using a solvent. Then after that, we dry the solvent, and they stay there. So now, this is now our material to capture CO2. And we have a solid material that has amine groups, but the chemistry is very similar from solid to liquid, or from liquid to solid. And for the first 10 years, this is what we did. We discovered some material. It's for anybody who's just a white powder, but that has the capacity to capture and release CO2, to capture release CO2 from mixtures and release pure CO2. Because people say, why are you capturing and releasing? We are capturing from a mixture, but we are releasing pure CO2. And then pure CO2, you can pipe it to somewhere and do with it many different things. I can show you later on what we can do with it, but we have too much of it. So most of it has to be sequestered, even though some of it can be used to make chemicals or to do enhanced oil recovery or things like that. Okay, so the first thing we did a long time ago, we optimized the grafting conditions. So I'm not going to go through the technical detail, but by doing that, we were able to increase the CO2 uptake by factor of 3. The next thing is when you remove CO2, you are using some gas mixture that are available that has CO2 and you want to remove it. All of these gases, they contain water. So even if you remove CO2 from air, it has water. From flue gas, it has water. From biogas, it has water. So we need to look what is the effect of water. So that is the first thing we need to do, because water is there everywhere. All these gases, they have some relative humidity. They have humidity, so we needed to look. And that's why our first paper was about water tolerance. That is our first paper 20 years ago. because there are some other very, very good adsorbents, but they are very sensitive to water. So in order to use them, we need to dry the gas, but that is out of any possibility. It's too expensive to dry air to remove CO2. Okay, so we need to use the gases as is. If they have water, so be it. Then you need to develop materials that are tolerant to water. Then we discovered that these materials are not only tolerant to water, they benefit by the presence of water in two ways. The first one, we found that water is actually a promoter of CO2 adsorption. And you can see the line that goes up, that is our material. When you increase the relative humidity, you can see your CO2 uptake increases. At least in this particular case, it increases by 25%. While when you take some other famous adsorbent like zeolite 13X, you can see it goes south as soon as you have water in your gas. So the chemistry for the promotion is shown there, but I promised not to talk a lot about chemistry. But there is some chemical explanation why water promotes CO2 adsorption, because it changes the chemistry to something more favorable. The other thing that we discovered later by sheer luck is that we wanted to look at how stable our material. So in order to see how stable our material, you need to cycle them, okay, to adsorb, desorb, and see what happened. And that's what we did, okay? So here, these are 5 experiments with 5 different material under 5 different conditions. But don't look at the detail. What you need to look at is how they are all decreasing. So my material is losing steam, is deactivating. Even under very mild condition, it is deactivating. And here I am using just a mixture of CO2 and nitrogen from a gas cylinder. So it's not even a real mixture, but it's a very simple mixture. And by luck, we humidified, we added water in the gas phase. And this is what happened. So everything got stable. So water has a stabilizing effect on amine groups, and that also has a chemistry origin. Under dry conditions, the CO2 itself is poisoning the amine by making some stable groups and removing the amines slowly in the form of groups that we call urea. Instead of this reversible chemistry, now we have an irreversible chemistry. And the origin of that irreversible chemistry is the absence of water. In water, it does not happen. That's why the materials get stabilized. And we patented that discovery, and we published it in a nice journal. And the next one, this is chemistry, unfortunately, but it shows you the red arrow leads to the irreversible chemistry. And you see that irreversible chemistry releases water. Then if you put water, then it will prevent it. So if you have water in the gas stream, you have the lower chemistry, what is written in the bottom of the page, and there everything is reversible. So everything is stable. So that is a very, very important role of water. Now, basically, even if you have dry gas, you need to humidify it. So water is no longer an enemy. It's on the contrary. We need water in the gas phase, first to promote the adsorption, and second, to stabilize the amine. Okay, I'll move on. This is too much chemistry, so I'm moving on. Okay, so this is basically summarize all the things that we've done the first 10 years and was mostly focused on the development of material. Then we said this material, it's not in the lab. It has to stay for a couple of days or 3 days. In industry, some industry, they want this material to stay there for 2 years. For 2 years, you are cycling, and every cycle takes 1 minute. They want 2 million cycles, okay, to get their money back. So we need very, very, very stable materials. But this process, especially the industrial process, is brutal. I will show you later what the material has to go through every single minute. So how much the material have all kind of resistance, okay, from chemical to against oxidation to mechanical to thermal to a lot of stability issues. So that the material has to be there and has to perform at least up to 80% to its maximum within a period of 2 years. So we try to look what are the effect of other impurities that we usually find in flue gas. Most of the work is done with flue gas in mind. Flue gas is the combustion gas in power plants. And you are combusting some fuel, and that fuel has nitrogen and has sulfur and has particles and has, so there are many, many different impurities. You could have H2S, like in biogas. You could have SO2, like in flue gas. You could have also nitrogen oxide. And we need to look at the effect of each one of these impurities. And the first thing we need to do, you can see in that right-hand corner in the bottom, we have to understand what happened. Okay, so we use all kinds of spectroscopy and chemistry and the mind of the graduate students and all that. Then we try to overcome this effect, and if we cannot, we try to mitigate, and if we cannot, we try to avoid. So these are the steps for these adverse effects. So I'm going to talk a little bit about SO2, because SO2, I think a lot of you are familiar with acid rain. That is SO2. So a long time ago, this flue gas was released as soon as you make your combustion. You just release it, and it has a lot of SO2, which combine with water in the atmosphere and makes sulfuric acid, and it drops as rain on forests and things like that. So since then, there have been legislation to remove SO2 from flue gas, but there are limits of SO2 concentration that you can release. But even at the ppm level, that's a part per million level, SO2 can be very harmful to amine groups because it absorbs, because first it is an acid gas, the same as CO2, so it absorbs as CO2, but it absorbs more strongly. Then it will poison your amine. So even if you have very, very low level of SO2, you need to get rid of it before you remove CO2 or before you capture CO2. So basically, we need to create a new material that we use as filter, that we use first to remove the SO2, then the rest of the gas will go to the material that is meant to capture CO2. So now we need to make a material that is selective, that even if you have minute amount of SO2 and large amount of CO2, it will go and pick the SO2 and let the CO2 through. And that's what happened by using one of the three amines, because I did not tell you that there are actually three amines. One is called primary amine, the one on the left, and it's based on the number of hydrogen that are connected to the nitrogen. So you see the one on the left has 2 hydrogen, that's a primary amine, the secondary amine. Those two, they absorb CO2. But the other one, the tertiary amine, it does not absorb CO2, but it absorbs SO2. So we said, okay, we're going to make a material that has only tertiary amine. And that's by just changing existing material. So for example, here you have different examples of material that has originally primary amine, Like, for example, this dendrimer that you see on the right-hand side, it has inside, it has tertiary amine. You can see every amine does not have any hydrogen, but it has a corona with NH2s. These are primary amines. And people who know organic chemistry, they can remove all these hydrogen and replace them by methyl groups. And now what you have on the right-hand side is a material with only tertiary amines. Okay, this is another example. This is yet another example that we did very, very recently. But all these are based on the same idea, how to make a material that has only tertiary amines. Because those tertiary amines, they selectively absorb SO2, but they don't absorb CO2. So when you have your mixture that has, let's say, 15% CO2 and 10 ppm of SO2, you have to run it through this filter, and it will remove that tiny bit of SO2, and the rest of it will be SO2 free, will go to the material that I talked about a while ago that captures CO2. Okay, but when we capture CO2, we need to use gases that are free of SO2, completely free, okay? Even if you have few ppm, after a while, they would have an effect, okay? So you can see here that we get the same, this 249 or 250, this is the SO2 capture, either as 5 ppm SO2 in nitrogen. There is no CO2 there. But after that, we add 50% CO2. So when you compare 5 ppm and 50%, there is the ratio of 10,000. There is 10,000 more CO2 than SO2, but yet we capture the same amount of SO2. So this material is extremely sensitive, and it will free your gas from SO2 completely. Then you can move to the next step. And you can use it as a filter in the same tower, so it will not be a separate process. This work on the oxidative degradation, okay? We are all very sensitive to oxidation because that's how we get older, because of oxidation, okay? So oxidation is the effect of oxygen. And as you will see later on the process, that there is one step where the material is in contact with air at high temperature. And that's where oxidation may occur. So we started working on oxidation. So this is different types of oxidation, different data on oxidation, and there are different temperature for different materials. And this is now probably the #1 issue that many academic labs and industries are working on, because it's very difficult to overcome, okay? So these are some oxidation product. It's also chemistry, so I'm not going to talk a lot about them, but just to tell you that everything we find, we have to dig and go to the bottom of it, okay? But I'm not going to talk about these things today. And now I move from my lab to outside my lab to tell you a few things that I know, but I am not part of it. Well, I'm part of it in discussion and in collaboration, but I am not in the bulk of it. Okay, so these are 3 among the most successful carbon capture companies, and they are all still in their infancy, okay, because they all started less than 15 years ago. Before, there was no industry for CO2 capture, okay? So for example, Svante, which is in our neighborhood here, started in 2007. Global Thermostat started in Georgia, 2009, and Climeworks started in Zurich. And all of these universities, they have roots in these companies, they have roots in universities. They actually use materials that were developed in universities by people like me who do not know anything about industry. Okay, that's so. For example, global thermostat, they are using materials that have been developed in Georgia Tech. Climeworks was started by two students from Zurich, but now each one of these companies is worth more than $1 billion. Okay, and there is a lot of public funding in this area right now. Because that is the only way we can develop this industry is by public funding. Still, the real industry still does not see the value or the opportunity for investment, for return on their investment. Okay, so this is the typical industrial process. It's in 3 steps. You absorb. Step 1, the CO2 at a relatively low temperature, usually from room temperature to 60 degrees. Then you regenerate the material at higher temperature, usually around 100, 110 degrees. Then you have to cool the material to bring it back to the original state, to reuse it. And this cycle has to be very fast, because we need to remove lots of CO2. So the material has to respond very quickly to all these events. Now, for regeneration at high temperature, the option, because at high temperature you can just heat, but in the industry, many industries, they opt to use steam, because steam is often available in power plants. And the other advantage of steam is that it heats, so it's the source of heating already, but when it takes CO2 with it, later on you have just to cool down and the steam will condense and you get pure CO2. So it's a very, very good solution to get pure CO2, is to remove it with steam, then after that you cool it and you get pure CO2. But then the material has to be stable in steam. So every step of the way, the material has to be stable under this and that conditions. And the cooling, now, since the material has been in contact with steam, it's going to be to heat up to 110 degrees, and you need to bring it to room temperature. And some industry, they are using the cheapest option, which is cool with air. But cooling with air is to expose the material at the highest temperature to the highest concentration of oxygen, because air has 21% oxygen. So you increase the oxidation opportunities. And that is where the problem is right now. So in my lab, we are doing a lot of work on oxidation and how to deal with it. Okay, so how does it work in real world? You can have your adsorbent in what it's called fixed bed, like in a tower, like the ones that you see in oil refinery. We put 200 kilo of material there. Then we bring those gases one by one. We bring the CO2-rich gas to adsorb. Then after that, we change it to steam. Then after that, we change it to air. So in this process, the material is fixed. That's why it's called fixed bed. And we change the flux of different gases to cover the 3 steps, okay? This is problematic because this thick layer of material creates a lot of what we call back pressure. So you need a lot of pumping and things like that. So it's better to change this system into what Svante is using. So Svante is using a rotor. You see this big wheel, and now they have wheels with larger and larger. I think their largest wheel now is 24-meter wheel, like this room or something like that. And you see the size compared to that big 18-wheeler. And that wheel is charged with the filters. You can see some schematic of the filter, and what is inside the filter are thousands and thousands and thousands of carbon sheets. And each carbon sheet has a layer of adsorbent. And between those two carbon sheets, you have 1 millimeter. And the gas will go through it, and you'll find the adsorbent on the left and on the right. Okay, so, and the gas can flow without resistance. That's the importance of these structured bed, what we call structured bed. It allows the gas first to be in contact with the adsorbent, but without strong resistance, like in fixed bed. And you can use either these carbon sheets. These carbon sheets are not done by hand. They are done by robots and stuff like that. So when you go to see their installation, it is like Star Wars or something, okay? So this is basically how it works. So you have this rotor in the middle, and you have those three now, those three gases are in fixed places, and they are running all the time. And it's the material that rotates. So the first, it rotates, and it finds the gas that contains CO2. It absorbs CO2. Then it moves, and it finds steam. Then it releases CO2, and it moves, and it finds air. Then it cools down, and so on. And this is now the cycle. So the cycle is the rotation. But now it is the material that rotate, and those three different gases, they are always running. And this is a much, much better system. Okay, you can see the cycle in the bottom, and it says 60 seconds. Well, obviously, mechanically, we can rotate this thing even faster. But the problem is the material has to respond, because we can run faster, but the material does not have the time to do its job. Okay, so the rotation is not limited by the mechanics. It's limited by the response of the material. Some other people use these ceramic monoliths, but it's the same principle, because these monoliths, they have these holes, and you build layer of adsorbent inside them, but they remain open. So the gas can flow through, and the gas will be surrounded by the adsorbent in every tunnel. Okay, and these are available commercially. So this is how it looks like. It's a real industry. See, this is how it looks like. And these are the filters, and they are done on a very, very large scale. And all this is just still demonstration scale. This is not real carbon capture. This is just to convince the world that there is something here, okay? So this is the rotation, and you can see now we have 4 steps. And there is one step that we want to remove. It's called conditioning. That's step 3. We included there, even though it costs money, because we cannot cool in air directly from step 2 to step 4, because we would expose the material to very high temperature, and the oxidation sooner or later is going to be there. And once you have oxidation, the material is dead. Okay, there is no reversibility there. Then we are, for the time being, we are adding one more step called conditioning, where we cool a little bit in the presence of nitrogen. So instead of cooling directly from 110 in air, we cool it, for example, to 70 degrees in nitrogen. Then we switch to air. And this operation costs money, because nitrogen is not as cheap as air. Okay, so these are some of the markets for CO2. So you can see you can have CO2 storage that is sequestration. Probably that is the largest opportunity for CO2, to get rid of CO2, is to sequester it. But then after that, you have a number of actual applications. So a lot of people, they tell you, oh, they can make jet fuel out of thin air. Okay, it's nice in a magazine. But in real life, it's so complicated. But there are people who are trying to make jet fuel out of thin air. You can make methanol with CO2. You can make, these are the regular chemistries of CO2. So once you have CO2, you can use it to make those. But instead of making CO2, you use the captured CO2. And there is CO2 conversion. You can convert CO2 into some other chemicals or polymers, but all these are small-scale applications. They have no relationship with the huge amount of CO2 that we have. Okay, but they are helpful. Okay, this is, I stole this from Svante presentation, and you can see the blue circle, that is what I talked about today in terms of industry. That is Svante job. My job is even on the left, okay? And you can see all the industries that you need to find all the way to sequestration. You need to have companies that replicate, for example, the Svante system once they have it approved. So, and you have to have people who operate it. Then you have to have people who commercialize the CO2 or piping and pressure, and there are all kind of things until you bring it to some place where you can sequester it. There are some places in Alberta, I've been told. Okay. I needed all these people to do the work. Okay, on the right-hand side, you have all the people that started from 2001 to 2024 to do this work, so I thank all of them. And you have the sources of funding from NSERC to iMACCS, CFI, NCE, Alberta Innovates, and Svante. And I would like to thank you. And if you have any questions, if we still have time, I'll be happy to answer them.
Thank you very much for this very nice talk. So there's 2 microphones, so people can stand up and Ben, just start. Welcome. Just join us. And I have a long list of questions in case, but...
That was really interesting. I have 2 questions. So the first one is, the whole reason we're doing this is because, you know, carbon fuels generate CO2.
Yep.
So, and the reason we use those is for energy. So what's the energy intensity for running one of these facilities, and where is the energy coming from? That's not, what's it being run, what are these factories going to be run on? Are they being run on clean fuel? Are they being run on solar or wind? So what's the net energy gain / loss from getting the carbon out of the air?
Okay, probably that question is beyond me because I'm the small university guy. So, but I can talk on behalf of Svante because I listened to their presentation, and they say the reason they are in Vancouver is because of the hydropower. So they are using the hydropower, but I agree with you that hydropower, you don't find it anywhere, everywhere. You need to have water. There are few places in the world where there is water. We see the plentiful of water in Canada, but this has nothing to do with the rest of the world. People are struggling to have water. So I understand. People, for example, they say you can use electricity from, yeah, these are all being developed. There is a lot of sun power. If that is harnessed, we can maybe make a lot of energy available that way. Unfortunately, most of the sun is in third world countries, so we need to go there and make energy. Something like that. It's a difficult topic.
So in their presentations, they say they're revenue neutral, energy neutral. Sorry, revenue neutral. They're probably revenue negative, but are they energy neutral? Svante, do they say their process is energy neutral or?
They try to be energy neutral, but I'm not sure you can. It's very difficult. A lot of people claim to be energy neutral. But when you dig, for example, people using electric cars, they say they are not producing any CO2, but they are.
Right. Yeah. That's why. Okay. So my other question is sort of maybe you can't answer this, as an expert, but the other, you mean as a biologist, obviously we always hear about photosynthesis, arrays being used to decarbonize. So do you have any comment on biological solutions for carbon capture, like photosynthetic arrays?
Yeah. There is a whole research area where they link biomaterial with CO2 capture, and it's a whole big area of research that I am not aware of the details of it, but it's there, and it's called BCCE or something like that. It starts from bio and it finished by CO2 capture, and it includes some bioenergy or biomaterial and things like that. Actually, we ourselves in the lab, we're trying now to make adsorbent based on biomaterial, not on inorganic material.
And that absorbent would actually, when you say you're doing that, are you trying to use like chloroplasts and actually take advantage of photosynthesis, or just absorbent material?
Actually, I'm doing it because there is the idea out there that those biomaterials, they are antioxidant by nature. So they may decrease this oxidation issue.